Hey everyone, this is Soma. I welcome you all to the first in series of videos in which I will talk about a research paper in less than 5 minutes. Me drinking a coffee while discussing those. I call it coffee with paper. Enough with the theatrics. Let's get along to what we are actually going to talk about in today's video. We're going to talk about word embeddings. Word embeddings are actually one of the most, I would say, successful applications in unsupervised learning. They do not require that expensive annotated data, but rather they require is unannotated data which is readily available. We can then use these pre-trained word embedding models to actually do a lot of downstream tasks using little small bits of data. We will get to that when we reach there. But as we start a journey of going through work done by great scientists and people around us, I start this journey with paper by Bengio et al. This paper is titled Neural Probabilistic Language Model. The paper is important because it lays down the groundwork. And not only it lays down the groundwork, it's the first time actually we used the word real valued word feature vector, and the model and the architecture suggested in this paper is actually the basis for the prototypes of all the current work that we have seen in NLP, especially around us. Diving further into the details of the paper, Neural Probabilistic Language Model, which was actually published in 2003 in International Journal of Machine Learning Research. The objective of the paper was to basically learn the joint probability function of sequences of words in a language. Roadblocks identified in that paper at that time were: first, cursive dimensionality; second, what if a sequence comes which we didn't see in the training data; third, computational expenses of training such a model. Existing best methods at that time was n-gram model. I must say that n-gram model is still one of the common techniques in NLP. So, what did the paper actually propose? Proposes to fight the curse of dimensionality by learning a distributed representation of words which allows each training sentence to tell the model about the exponential semantically neighboring sentences. This is pretty awesome. The model thus learns two things simultaneously. One is a distributed representation of each word. Second, the probability function of word sequences in terms of these representations. Next, we're going to talk about the scope of the problem. So suppose you want to understand that what is actually the scope of a problem. If you want to model a joint distribution of 10 consecutive words in a natural language which has a vocab of size 100,000, it would be equal to 100,000 raised to the power of 10 minus 1 free parameters. Thus comes the statistical language models. Statistical language model basically is represented by the conditional probability of the next word given all the previous words. These kinds of models are very common in NLP processes. N-gram models basically construct tables of conditional probabilities for the next word for each one of large number of contexts given the last n-1 words. The major challenges that actually arises in this model, as said in the paper, are they do not talk about taking into context more than 1 or 2 words further. They do not talk about similarity between the words. We're going to talk about similarity more shortly. And it doesn't talk about challenge in training such a very big neural networks. Talking about similarity, let us take an example. The cat is walking in the bedroom. In the training corpus should help us generalize any other sentence of similar semantic nature. For example, a dog was running in the room. So what does it mean is that if I have a sentence, the cat is walking in the bedroom, I should be able to generalize dog was running in the room, because dog and cat are semantically same, and hence room and bedroom are semantically same. So how does the paper work through this? Paper says, let's put 3 basic steps for solving this problem. These are not so basic, but yeah, 3 steps. So in a nutshell, they say that associate each word in vocab with a distributed word feature vector, which is a word vector in a real space. Second, they express the joint probability function of word sequences in terms of feature vectors of these words in sequence. Third, learn simultaneously the word feature vectors and the parameters of that probability function. Alright, this is sounds like a lot of technical, but what did actually we get from all of this? What we actually get from all of this is, one, a feature vector, which is basically a word feature vector, which the number of features are the important point is this: number of features is very small as compared to the number of words in the vocabulary, and this gives us high computation efficiency. Second, presence of only one of the sentences in the training data will help us increase the probability of inferring any semantically neighboring sentences. For example, the cat is walking in the bedroom. We should be able to generalize as able to dog was running in the room, the cat is running in the room, a dog is walking in a bedroom, the dog was walking in the room. All this from only one sentence present in the training corpus. Okay, so let's go into deep dive of the implementation details proposed in this paper. So what we have in start is a sequence of words, W1 to WT. Now, each of the word basically belongs to the vocab of the natural language into consideration. What we are aiming for is to model a function f, which would basically give us the probability of word t given all the previous words in the sequence. Now, how will we do this? We create a mapping C, which is from every word in the vocab V. We basically translate that into a real vector Ci, which is in real space, and we call this vector as distributed feature vector. In general, the C, which you see, is basically a matrix of size V cross M, where V is the size of the vocab. Now we go further into details and we come up with function G, which basically takes input of sequence of such vectors and give us the function F, which we are aiming for, which would in turn give us the probability of word T given all the previous words of the mapping. Now, as you can see in this diagram, basically sometimes these word input feature vectors are directly connected to the output, and sometimes they go through one more hidden layer. So basically our neural architecture basically has got 2 hidden layers, and we use a softmax layer, which basically softmax layer for the output, basically guaranteeing us the sum of all the probabilities come to 1. We do the training as in any neural network by maximizing the training corpus, penalized log likelihood, and going over the parameters using a stochastic gradient descent method. But what's really important is that we will be able to represent the output in terms of concatenation of the feature word vectors. I think that's all for the implementation details of this paper. What were the results of using such a model? The results of using such a model is this model, especially the neural network based models, actually proved out to be better than best of the n-gram models. So there were 2 tests done in this paper, one on the brown corpus and one on the AP News corpus. It was supposed to be 24% better on the brown corpus and 8% better on the AP News corpus. So before I finish this, I really want to talk about the key takeaways that we actually come from this paper. As I started with earlier, the key takeaways are the model scales linearly with V, which is vocab size. It scales linearly with order n, but it could be reduced to sublinear by using some sharing structure. So this actually lays basis for all the current work, which is like use of LSTM, use of time-delayed neural networks. Third thing, which they identified for softmax, is the bottleneck, as it's proportional to the number of words. I hope you guys enjoy my explanation of this paper. Let me know if I could have simplified this paper more, or details I should have gone deeper into. Any feedbacks on the video and how could I improve would be really helpful. Also the type of content on any specific areas of NLP or deep learning that you would like to see in these videos. That's it for all. I hope you guys enjoyed your coffee. I did mine. Thank you.